Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over alpha alkylation and acylation. Okay, so this is section 5, and basically we're kind of moving our way towards the end of the chapter. Not much more to go. I think there's like 7 sections in total. After this video, we'll do our next problem set. This will be our second problem set, okay? And it'll cover halogenation as well as this material here. Okay, so now looking at this here, we have a few things to cover, and the first thing is shifting the equilibrium. Let's talk about what that means. So now we know that when we're talking about, let's say, reactions that are taking place in this chapter, let's say we're looking at a dicarbonyl. So we have this beta diketone, right? Now I know that if I use, let's say, hydroxide with this, then I'm not going to have a problem making it into an alpha anion. And the reason why is because of the pKa difference between the two sides. Remember how we did this last semester? We said that you always look at the pKa for each acid. Now, this carbon has one more and this has one less H. So this is the acid, pKa 9, and this is the conjugate base on the right. Whereas hydroxide has one less and water has one more H. So water is the acid, right? Now we always go from the lower to the higher number. So I know that this is actually favoring the forward direction. So if I want to remove a proton from this alpha carbon, I could do that very easily with hydroxide. Okay, because this is a smaller number, it's more acidic. So we don't have to worry about this one reprotonating here and going back. Does it happen? Sure it happens, but not as much as it goes forward. Right? So this doesn't require a shift of equilibrium. We actually want to go in this direction. So this is perfect as is. Now, why do I show this to you? Because when we look at a ketone and we treat that with hydroxide, okay, or any kind of, let's say, ketone, aldehyde, any of the structures that we've discussed in our review video so far, okay? So if we have this as example ketone, now the ketone becomes an alpha anion, right, plus water. And again, if I do my pKa consideration, then I recognize that this is around 19. I'm going to say 20, because that's what I did in my notes. It's like 19 to 20. Doesn't matter, one of those two, okay? And now over here, this is 16. Now clearly, the direction is in the wrong place. See, if we're going to go and try to pull off an alpha H, we can't do that very well with a hydroxide. Now, it turns out that for halogenation or for deuterium exchange, it's fine, not a problem. So we can wait, and through time, it will happen, okay? But if we want something a little bit more aggressive to take place, something that's a little bit more important to us, but not so much that you can deal with, like a solution with water is something that just naturally happens by itself. You deprotonate and you reprotonate. So like deuterium exchange or you know, going through racemization, those are things that really just happen naturally. But if we want to build carbon systems together, we want to build up molecules, then this is something that we're intentionally trying to do, and we need to do it a little bit more aggressively than what hydroxide offers. Okay, so what we found is that if we try to alkylate, which is the topic of this video, right? Alkylate and acylate. That if we use hydroxide, it doesn't work very well at all. It does on top because we can get alpha anion very easily, but it does not on these monocarbonyl groups, whether it be a ketone, an aldehyde, an ester, an amide, doesn't matter. They all have the same issue. So what do? Well, it turns out that what we need to do is, so let me write this down, in order to alkylate monocarbonyl compounds, we need a stronger base. Okay, that's what we need to do. We need a stronger base. And that'll allow us to alkylate, because then we can actually get the alpha carbon to lose its proton in a much higher yield than it does now. Remember, we said that this is around 99% of the time how it's going to look, whereas this is around 1% where it's going to look like that. We don't want 1%. See here it's like 76%, remember on top? So that's good. This is bad. So what we're going to do is we're going to use an aggressive base, something a little bit more, a lot more powerful than a hydroxide. Something that's going to be a lot less conjugate acidic than the ketone would be, okay? So what we're going to use is called LDA. So if we treat this with LDA, and we check out the difference now, nitrogen that has diisopropyl twice, remember this, we talked about LDA before, so this is, let me clean it up, so lithium diisopropyl amide. So this nitrogen has 2 lone pairs, it's negative, and there's a lithium hanging out next to it that's positive. That's LDA. Okay, so LDA is lithium diisopropyl amide. And amide, you might think amide, isn't that a carbonyl with a nitrogen? Yeah, this is kind of one of those things. Nitrogen that's negative is called an amide. Okay, so it's contradictory to the amide that we're used to thinking about, right, from this chapter 17. Okay, so when we look at what happens here, we're going to, again, just deprotonate the carbon, and we're going to turn LDA into this amine, okay, this diisopropyl amine. Now, when we look at the pKa, right, so pKa here is still 20, right, 19, 20. This right here, pKa is 35. So notice that the conjugate acid is much, much, much more basic, right? It's a much weaker acid than this one. So this for sure is going to completely dissociate, or sorry, it's going to completely deprotonate the ketone and make it into this right here. So we've just shifted it. So now this is around 99% of what it's going to look like. We've shifted the equilibrium. You see that? So that's the key here is how do we do that? And we do that with LDA. Now, here are the 2 benefits of LDA. So here are the benefits. Number 1, we get a lot of alpha anion, which is what we need for the next step. Number 2, LDA is bulky. Okay? So it will not attack the carbonyl carbon. See, that's important to keep in mind. See, if nitrogen is a good nucleophile as well, so if we're not careful, this nitrogen can come into this carbonyl while this opens up, and then we'll make something called an imine or an enamine. In this case, it would be an enamine, but we're not going to have to worry about that because it's not going to come in. Okay, so this nitrogen is not going into the carbonyl, neither is that one. All right. So that's the benefits. So LDA presents a very good opportunity for us to actually use something that gives us a much more appreciable amount of alpha anion. So now what's going to happen now that we know that we can make alpha anion? What are we going to do with this information? Well, here's what we're going to do. And by the way, let me just, one more thing I want to point out. Why do we get a lot? Because LDA is a strong base. I want to make sure that I'm making that clear. That's why we get a lot of alpha anion, right? Because LDA is a strong base. Okay, so what do we do now that we understand why we might turn our attention away from hydroxide into something else? Let's talk about the reaction itself. So the first thing I want to talk about, A, is alkylation. Now, alkylation requires a base environment to get this done. So you have to, with a ketone, with a carbonyl, okay? A carbonyl, because we're going to be more generic. Right now we're learning about ketones and aldehydes, but this could be any any carbonyl that we've discussed. What's the only exception? The ones that never react in this chapter: carboxylic acid, an amide that has an H on it, and a thioacid, right? Those are the 3 that are not alpha acidic ever. So those are the only ones that don't work. Otherwise, we could do them with all the others, okay? So we're going to start with ketone, but realize this is just our model. Okay, so let's say we have a ketone, and we want to, let's just make it like this, like something like that. And notice it's symmetrical. We'll talk about when it's not symmetrical next. So if we start by using LDA, then we're going to get our alpha anion. Okay, and now from here we can add into this RX. Now the key is R equals a methyl, a primary. Now, it can't be secondary. It cannot be secondary. Okay, so it's methyl primary or allyl. Okay, never